All right, welcome into our Chapter 6 material, continuing on with our acid-base chemistry in the context of equilibria. In this chapter, we will get into our buffer solutions, including the Henderson-Hasselbalch equation, and titrations for weak and strong acids combined with strong bases. All right, buffers are going to be solutions that are able to resist changing their pH. Very useful solutions, whether that's for biology in our cells to keep the pH from going into dangerous levels, or perhaps in manufacturing, or perhaps in a lab setting where keeping the pH at a steady range is very important. The way that our buffers work is by having both a weak acid and its weak conjugate base present in the solution at the same time. We can visualize this here. If you combine a weak acid and its conjugate base into the same solution, here's a bar graph. We have both an acid and a base present. This allows us to resist changing the pH if any other acids or other bases get added. If we have our original buffer, conjugate acid, conjugate base present, what happens when strong base gets added? Well, if strong base gets added, we can use up some of our acid that's present. It can neutralize it with the acid that's already there. Likewise, if any acid gets added, we do have a base that's present that can neutralize that new acid. In terms of Le Chatelier's principle, we have this equilibrium with both a weak acid and its conjugate base present. We'll have some amount of H3O plus in addition to our conjugate acid-base pair. If you add any strong acid or add any strong base, you'll change the amount of H3O plus that's present, but since we do have both other reactants and products present, we're able to shift easily left or right to counteract that disturbance. If we want to be quantitative, well, our same strategies hold true. We can use our ice tables to solve for the pH of our buffer system. Here's an example. We have 0.2 molar of this acid and 0.15 molar of its conjugate base. We know the Ka value. Can we figure out the pH of this buffer? In order to reach our equilibrium, we're going to have to form at least a little bit of this H3O plus, and we can use these values in our Ka expression. If we want to be generic, we can use our symbols here. And let's do a quick derivation here. If we're trying to solve directly for the pH, we can do that. We can just take the negative log of both sides. On the left side of the equation, we have negative log of our Ka. We call this the pKa. On the right side of the equation, we have negative log of a lot of concentrations. If we remember some log arithmetic, if we take the log of some terms that are multiplied together, we can change those into separate logs that are added together. Here we can separate out our log of H3O plus or H plus and our log of the other concentrations, A minus and HA. The negative log of our H3O plus, this is exactly the same as our pH. We end up with this expression, which can be slightly rearranged to be a solution for exactly the pH. What we get if we solve this ice table is that X is 2.4 times 10 to the negative 4, and our pH is 3.62. If we want to use this other expression, we could also use that. The pH is equal to the pKa plus the log of conjugate base divided by conjugate acid. This is a special case. It's the solution to our ice table, but it's the solution to our ice table when we have both a conjugate acid and its conjugate base present in the same solution. This is known as the Henderson-Hasselbalch equation, and it's really useful as a shortcut for finding the pH of that system where we have both an acid and its conjugate base. exactly for when we have buffers. Notably, this is the same as our ice table math. It's just rearranged slightly. And it does only work when that small x assumption is valid. We need to have both our conjugate base and our conjugate acid, and we need to have that small x assumption be true. If that's the case, though, it ends up being a nice little shortcut. There is a special situation when we have buffers. Mathematically, the log of exactly 1 is equal to 0. If we have equal amounts of our conjugate base and conjugate acid, that ratio is exactly 1, this log is exactly 0, and our equation simplifies down to just pH is equal to the pKa. What that means is when we have a buffer solution with exactly equal amounts of conjugate acid and conjugate base, our pH is exactly equal to the pKa of our acid. This is cool. Different acids have different pKa values. Different acid-base systems can form buffers with different pHs. If you want to design a buffer with a pH of around 5, choose a weak acid with a pKa of approximately 5. If you want a buffer with a pH around 9, great, choose a different weak acid with a pKa of approximately 9. Our buffers won't always have their pH exactly equal to the pKa. We can fine-tune this by changing the amounts of conjugate base and conjugate acid slightly so that we have more of one than the other, and shift that pH away from the pKa by at least a little bit. As an example, we can find the pH of this buffer solution with 0.1 molar ammonia and 0.2 molar ammonium. We know the Kb value for ammonia, or alternatively, the pKb value. Two options for solving this. Since we have a buffer system, we can shortcut and use our Henderson-Hasselbalch equation. Alternatively, our ice table strategy from before will be good, it will still work. To highlight our new strategy, we can write out our equation, and we can start to fill in the values that we know. Notably, we're given the pKb value, so we can find our pKa value using our Kw equation. If the pKb value is 4.75, the pKa for its conjugate acid has to be 9.25. There we go. The Henderson-Hasselbalch equation, faster than finding the answer via an ice table a lot of the time. Although it is the same math, you will get the same answer if you prefer to use ice tables. Notably, we expect our buffer to have its pH around the pKa value, which is around 9.25. But we have a little bit more of our conjugate acid compared to our conjugate base. Therefore, our pH is going to be a little bit less than, a little bit lower than our pKa value. And that is what we see, 8.95 compared to the pKa of 9.25. Our buffer will resist changing its pH, but it won't necessarily completely stop changing its pH. When we add a strong acid or a strong base to a buffer solution, we call this a buffer challenge. If a strong acid is added to our buffer, our conjugate base is converted into the conjugate acid, and our ratio of conjugate base to conjugate acid has been changed. Alternatively, if we add strong base, our weak acid is converted into its weak conjugate base, and again, our ratio tends to change and needs to be recalculated. The pH will change slightly, but not dramatically. If we want to deal with this quantitatively, we want to break our calculation up into two different steps. First, we can think about stoichiometry, a complete reaction between our strong acid or base and our buffer system. Step 1, what reaction can occur? Step 2, once we do a complete reaction, then we can establish our equilibrium based on those new concentrations. This is purely a mathematical trick to make our calculations and our lives easier, so it is the way I recommend solving these problems. Here's an example. We have our certain buffer situation as explained above. What happens when we add 0.005 moles of our strong acid? We can draw a picture. We have our weak acid and its conjugate base both present. Now we add some HCl. That chloride is going to be neutral, but our H+ is able to react with one of our things in our buffer system. If we have H+ reacting with our conjugate base, the product has to be our conjugate acid. We want to consider this reaction to go to exactly completion based on our limiting reactant. Using the given volumes and concentrations, we can calculate exactly how many moles of our conjugate base and conjugate acid we're starting with, and fill those into not an ice table, but a kind of stoichiometry table to figure out our final results after this complete reaction. The moles present will be our volume times our concentration. In our beaker, we have 0.005 moles of H+, 0.0625 moles of our conjugate base, 0.0625 moles of our conjugate acid. If a complete reaction occurs, we'll use up all of that H+. What we're left with is none of our H+, less of our A-, and more of our HA. This is our complete reaction. We're not at equilibrium yet, but we've done a complete reaction between whatever we added and our original buffer. Now we can re-establish our equilibrium. We have a new buffer with slightly different amounts of HA and A-. In our equilibrium system, we have some molarity for our weak acid, we have some molarity for our conjugate base, pulled directly from the end result of our first complete reaction, taking into account that our first table was in units of moles for stoichiometry, and our equilibrium ice table needs to be in units of molarity. From here, we can solve either by doing that ice table calculation or by doing our Henderson-Hasselbalch equation. Take your pick or do both. Our answer will end up as pH equal to 4.67. If we want to consider buffers qualitatively without calculations, we can also do Le Chatelier's principle. Buffers are an example of the common ion effect. If we are trying to establish an equilibrium, we can have maybe just a weak acid reacting with water. It will dissociate, ionize into H3O+ and its conjugate base. Well, now think about trying to do that same reaction if there is already some product hanging around. This is a classic example of Le Chatelier's principle. We're trying to do an equilibrium, but with extra product hanging around. Well, our equilibrium position has to shift to counteract that. If we have both our acid and our base present, the reaction will shift to the left compared to the situation starting with only our acid. Right? Adding the conjugate base disturbs our equilibrium, and we need to counteract that by shifting over to the left. The common ion effect is basically just Le Chatelier's principle, trying to perform a reaction when there is already one of our products in our system. In the case of buffers, we're doing our acid dissociation when there's already that conjugate base present. Our buffers will have a pH that is higher than if we had just the acid by itself. Another property of buffers that we can examine is the buffer range. Our buffers can only keep their pH constant over some range of pHs. This is only going to be true when we have that about 5% rule holding true, that small x approximation being true. Our buffer range is going to be approximately 1 pH unit above or below our pKa value. Outside of that pH range, our buffer won't be as effective, and the pH will start to jump around with challenges of acid or base. Another property of our buffer is the buffer capacity. The buffer capacity is a metric for how much acid or base can be added before we get out of that buffer range, right? Before our pH starts to meaningfully change. We can compare two buffers, right? If we have our bar graph over on the right, this top buffer has a small amount of conjugate acid and conjugate base, as opposed to our bottom buffer, which has a large amount of our conjugate acid and conjugate base. This bottom graph, it has more conjugate acid and conjugate base present to deal with any challenges. This bottom situation will have a larger buffer capacity. One last practice question. We can try to sum together our ideas about buffers. Can we design two different buffers that have a pH of 2.75? Exactly how much of each chemical do we need? Exactly which chemicals do we need? And keep in mind, there's going to be a bunch of possible answers. Depending on which system of acid and conjugate base we choose, we might need to have different amounts of them to reach that pH of about 2.75. Notably, in order to have a buffer with a pH of 2.75, we need to have our pKa within about 1 pH unit of that 2.75. So while we do have many choices, there are not infinite choices. If I choose to build a buffer with nitrous acid, the pKa is 3.34. We're going to need to have extra of our conjugate acid to lower our pH down to 2.75. The exact amount of acid and base can be described using the Henderson-Hasselbalch equation. We can do a little bit of algebra here and figure out exactly that ratio. For the system that I'm building, we're going to need to have our base compared to our acid be a ratio of about 0.257, or mathematically less of our conjugate base than our conjugate acid. All right, one last big topic we can discuss in this chapter. We can think about titrations, acid-base reactions combining together to neutralize each other. Titrations we've seen before already in our class. This is a nice way to quantify how much of something is present. The idea is that we can combine our reactants together slowly and stop once we know that the reaction is complete. This is known as the equivalence point when we have exactly stoichiometric moles of our reactant. Or experimentally, this is known as the endpoint when we're able to detect that we should have stoichiometric moles of our reactants. In theory, we want our endpoint and our equivalence point to be as close as possible. In practice, it's not always perfect, but usually we can be pretty good. The simplest titrations we can think about are strong acid and strong base titrations. Here we're combining, like it says, a strong acid with a strong base. When we are at the equivalence point, we have exactly stoichiometric moles of our reactants, and they neutralize each other completely, forming water and a neutral salt. For our strong acids and strong bases, the salt that is formed is going to be exactly neutral. The cation from our strong base will be inert. The anion from our strong acid will also be inert. Therefore, we expect our pH to be exactly 7 at our equivalence point. If we graph our pH every step along this way, we can call this a titration curve. It has this characteristic S shape. The pH changes drastically around this equivalence point and much more slowly before and afterwards. To measure our endpoint, we can use a digital pH meter. That's a great way of doing it. Or if we want, we can use an indicator molecule, which only changes color around a certain pH. A common one is phenolphthalein, which turns pink around pH 7 or 8, allowing us to measure some endpoint. Since this pH curve is very steep near the equivalence point, our equivalence point and our endpoint should be very close to each other in terms of the volume of base added. We have used phenolphthalein perhaps in lab in the past. This is the one that turns this nice bright pink color. There are a variety of indicator molecules, however, which are useful in other circumstances. Choose an indicator molecule that will change color around the pH range that you want to detect. The reason that these indicator molecules work is that they themselves are weak acids or weak bases, where they are converted from the conjugate acid to the conjugate base or vice versa. One of these forms has a certain color, the other has a different color. Phenolphthalein, for example, has a pink form in basic conditions and a colorless form in acidic conditions. As we said, we can keep track of our titration using this titration curve. At the beginning of our strong acid, strong base titration, we only have our acid. The pH is going to be low. As we add more of our base, the pH increases until we reach the equivalence point, at which point the pH is sharply increasing. Past the equivalence point, we have excess base, and our pH will be dictated purely based on the amount of strong base that's in excess. If we'd like to do our numerical calculations, we certainly can. We can break this up into two steps, just as before. We can do a stoichiometry step, and then perhaps consider any equilibria that might show up afterwards. For strong acid, strong base calculations, well, maybe there's not too much of an equilibrium to worry about, but we can certainly use our ice table setup to organize our stoichiometry. For our stoichiometry, we can be in units of moles or perhaps millimoles. Try to do a complete reaction, see what is in excess. Our excess amount of strong acid here will therefore dictate our pH. 0.5 millimoles of acid in a total volume of 11 milliliters leaves us with a concentration of 0.0455 molar. With that concentration, we have a pH of 1.34. Notably here, we've neutralized half of our strong acid, but the pH is still extremely low. If we wanted to do this calculation at other steps along our titration, we certainly could do exactly the same steps. Set up your stoichiometry table, figure out what is in excess, and the pH will be dictated by that. We can move on to think about our slightly trickier titration setup, where we might have a weak acid reacting with a strong base. We can still keep track of our titration using this titration curve, graphing the pH every step along the way. But the math is going to be a little bit more involved because we'll have to deal with equilibriums. At the beginning of our titration, we only have a weak acid. We can deal with a weak acid by itself using our regular ice table strategies from before. As we start to add base to our acid, we can neutralize some of it. When we have some of our acid neutralized, it will turn into its conjugate base. We'll have a mixture of weak acid and its conjugate base. We can form a buffer partway along our titration. As we continue, we'll approach the equivalence point. At the equivalence point, we will have all of our weak acid converted into its conjugate base. What's left is a weak base, which will reach an equilibrium with a pH above 7. The equivalence point for our weak acid titration will no longer be neutral. Instead, it will be slightly elevated. Past that equivalence point, Well, this behavior is kind of the same. When we have excess strong base will dictate the pH. We can run through an example here. With a weak acid and a strong base titration, well, before the titration starts, what is our pH? We can just do a regular ice table calculation. 0.1 molar hydrofluoric acid will reach its equilibrium, and we can solve this problem. Solving our ice table, we know the concentration, we know the pH, 2.23. Partway through our titration, we can also do our calculation, although it's helpful to break it into two steps. Can we first do a complete reaction and follow that up by thinking about our equilibrium? If we have 10 mils of our 0.1 molar hydrofluoric acid and 3.5 mils of our 0.15 molar sodium hydroxide has been added, we can do our stoichiometry in terms of moles. Take your volume and your concentration. If you multiply them together, you'll find out how many moles or perhaps millimoles might be there. With these amounts of weak acid and strong base present, we can neutralize exactly 0.525 millimoles of our weak acid and create 0.525 millimoles of our weak conjugate base, which we can then use to consider our equilibrium. For equilibrium, we have a couple of choices. We can set up our ice table. Probably a good idea to convert into molarity for our ice table, and then solve for X, solve for our pH. Alternatively, since we are in the buffer region, we are in a situation where we have both our weak acid and its conjugate base present. We can skip ahead and use our Henderson-Hasselbalch equation, where the pH is equal to pKa plus the log of this ratio of concentrations. We can look up our pKa value, plug in our concentrations into that equation. Notably here, actually the final volume doesn't matter if we're in units of millimoles or in units of moles or in units of molarity in our Henderson-Hasselbalch equation. That volume actually cancels out. It doesn't matter if we include it. We have 13.5 milliliters at this point in our titration. If we include that volume in our equation to get to concentrations, well, it doesn't really matter. Dividing both the top and the bottom of that fraction by 13.5 cancels out. At this point in our titration, the pH is close to our pKa, but a little bit higher, 3.50. Our last calculation example, we can consider what happens exactly at the equivalence point. If we have 10 mils of our 0.1 molar hydrofluoric acid with 6.67 mils of our 0.15 molar sodium hydroxide, this is stoichiometric amounts. We should have equal amounts of our weak acid and strong base. Again, let's do our stoichiometry first. If there is a complete reaction, we'll use up all of that weak acid, all of that strong base, turn it all into our weak conjugate base. From here, we do have to consider our equilibrium. Sodium fluoride is a weak base salt solution. To solve this equilibrium, we have 1 millimole of our weak base in 16.67 milliliters total, and we can look up our Ka value for our acid. Okay, great. That will tell us how to find our Kb value, and we can solve that ice table. I'm going to leave this example as practice, but if you want to check your answer, we should get a pH value of about 8.12, which is what we'd expect. Our equivalence point is going to be above a pH of 7 when we have a weak acid, strong base titration. Going back to our titration curve, we can identify a special point on this curve. In our buffer region, there is exactly one point on our curve where the pH will be exactly equal to our pKa when we have exactly equal amounts of our conjugate acid and our conjugate base. This is what happens when we have neutralized exactly 1/2 of our starting acid. Half of it is still acid, the other half has been converted to base. When you are exactly halfway to the equivalence point, we call this the half equivalence point, our pH will be exactly equal to our pKa. This is useful. This is a distinguishing characteristic of our various acids. If you want to determine the pKa of your weak acid, you can do a titration, measure the equivalence point, and then measure the pH at half that equivalence point. Fantastic. Finding the pKa will give you some hint as to what your weak acid might be. One last wrinkle on our titrations. We can also have polyprotic acids. In the case of polyprotic acids, our titration curve will look similar, except it won't just level off completely at the end. We can reach a second equivalence point as we neutralize that second proton. Essentially, our titration happens stepwise. We'll neutralize that first acidic proton completely first. Then we can move on to neutralizing our second acidic proton, or third, or fourth, however many acidic protons we might have. When we have polyprotic acids, we will have multiple equivalence points, multiple buffer regions, and multiple pKa's that you might be able to determine. If we're trying to solve these polyprotic acid problems quantitatively, well, we have our ice table strategies. We can deal with the strongest acid or base first, use that as our first approximation, and move on to our weaker and weaker acids and bases afterward. There we go. We've reached the end of our section on titrations, a nice laboratory technique for determining unknown concentrations. But now we know even more. When we have weak acids or weak bases, we can use our known strategies for solving these problems quantitatively, just as we have in the past, by breaking it up into perhaps 2 steps, a stoichiometry step and a equilibrium step. That's what we have for today. Thanks for being here. Please let me know if you have any questions. Look forward to seeing you in the next video. Have a great day.